Hello students, next we are going to look into the fundamental sensor methodologies. That means we are looking into how the sensors can be classified according to the type of energy that they try to detect. When we discuss this, we will understand that there are many sensor classifications through which we can get many different kind of sensors. For example, we start with thermal engineering. Thermal energy, sorry. So when we want to measure temperature or the flux or conductivity, that is heat conductivity, and the specific heat, we basically want to measure the thermal energy. And the various sensors for measuring the temperature are basically thermometers, thermocouples, thermistor, and for heat, for measuring the heat, that is in joules, we basically use the calorimeter. So here what you should remember is that here we are basically measuring either the degree Celsius or the degree Fahrenheit, whereas here we are measuring the heat energy or the calorie, which is basically in joules. The next classification is the electromagnetic energy, from which we have the electromagnetic sensors, which basically measure the voltage, the current, the charge, the magnetic field, magnetic flux, and permeability. The resistance sensors basically measure what is the resistance for the flow of current, and basically we have for that the ohmmeter and the multimeter. Similarly, to measure the electrical current that is flowing through any conductor, we basically have the galvanometer or the ammeter. The galvanometer will only give the direction, and it will not give the exact value, whereas ammeter will give the exact value of current that is basically flowing. So galvanometer is mostly used for detecting the presence of current, and ammeter is basically for measuring the current. Similarly, if we want to measure voltage, we have the voltmeter, and if we want to measure the power, the watt hour meters that we are having, especially the meter that we are using in our homes to measure the units of power that is consumed, that is basically the watt hour meters. Similarly, for magnetism, we have magnetic compass. Again, magnetic compass, just like galvanometer, will only give the presence of magnetic field, whereas magnetometer will basically calculate how much is the value of magnetic field. And similarly, the Hall effect devices also, like magnetometer, will give how much amount of magnetic field is present. Next, we have the mechanical sensors, which are basically for measuring quantities such as the position, the shape, the velocity, force, torque, pressure, strain, and mass. So all of these are mechanical quantities. And for measuring pressure, we will basically have barometer or the barograph or the pressure gauge or even the airspeed indicator. For gas and liquid flow, basically we have the flow sensor, the flow meter, the gas meter, the water meter, and even the strain gauge. Next is the case of chemical sensors. For that we have the ion selective electrodes, pH glass electrodes, etc. Whereas for optical and radiation sensor, we have the bubble changer, the dosimeter, photocells, photodiode, phototransistor, photoelectric tubes. Now coming to the acoustic sensor, which basically measures the acoustic energy, that means the sound energy. They are basically the microphones or the mic, the hydrophones, which are basically dipped in medium like water and trying to catch the acoustic wave that is passing through the water. Then seismometers. Now let us look at many of them one by one. We'll start with the temperature sensor. So the commonly used sensors for temperature measurements are basically RTDs, which are the resistance temperature detector, the thermocouple, the thermistor, and some fiber optic temperature sensors. We will be basically discussing only the first three. Starting with the resistance temperature detector. Resistance temperature detector is basically a kind of resistor whose resistance value changes, and it changes with respect to the temperature around it, which is called as the ambient temperature. So based on the ambient temperature, the value of resistance of this RTD or the resistance temperature detector basically changes, because of which the current that is flowing through it, that changes, and that can be calibrated to find out what is the temperature or the ambient temperature accurately. One of the methods to actually measure this is using a bridge circuit. What is a bridge circuit and all we will study later. Now, how does the temperature of a how does the resistance of a material change with respect to temperature? If you remember, any material basically consists of elements which have free electrons or valence electrons which can move around. Those valence electrons or the quantity of the valence electron is basically dependent on temperature. Based on the temperature, the value of the number of conductors that are flowing in a conductor will basically change. So using that principle, if you are going to have a particular conductor which is very sensitive to temperature, that means its value of conduction electrons, or even semiconductor materials which are having holes. So semiconductor materials will have charge carriers like holes and electrons. So any material whose carrier concentration changes with the temperature can be used for detecting the temperature. Here you are seeing a basic construction of a RTD, and here you can see that there is a resistance thermometer part where you are having basically a conductor wire which is wound in this way. It is basically wound in long length. That's why it is wound in this particular shape, so that you get a good length of the wire. Why? Because the change is very, very small. So if you take a very lengthy wire, then only the change will be visible. With the length of the wire, the resistance changing per unit length is very small. So if you would keep a very lengthy wire, the good thing is that the change will be more, and it will be more sensitive. So here we see that length of wire is basically shown here, and then the two connections which are basically insulated using an insulator, and a sheet that covers on top of it is also shown. The common materials that are used, the metals that are used are basically platinum wires, nickel, and also copper wire. And platinum is the most commonly used, but we know that platinum is slightly costly. And platinum, one of the major reasons for it being used so commonly is its stability and nearly linear temperature reading. It can read or measure up to 800 degrees Celsius. The RTD is basically known as a absolute temperature device. What is an absolute temperature device? It gives the absolute value of temperature. It does not give the relative difference between 2 points of temperature. That means suppose you are having some temperature, some 0 degree, and then you are measuring temperature, and then you take the difference between the two, and then that becomes the reading. It happens in case of thermocouple that we will study later. So if you would ask what is an absolute temperature sensor, then that is a RTD, which basically gives the absolute reading. Here we can see some of the images of various types of RTDs that are available in the market. The advantage is that it is very stable and accurate, and as compared to thermocouples it is more linear. The disadvantage is that it is very expensive. It's more expensive as compared to thermocouple, and it is self-heating because there is a current that is passing through. I told you that RTD basically works on the principle of how much amount of current is passing through. That current flow through the device itself creates a heat, and that is basically a self-heating phenomenon, and because of self-heating there will be a change in the original reading of the temperature. Another thing is that it requires a current source. Again, since it's a resistance, we are passing currents through it, so there has to be a current source, and the response time will not be that fast because it takes some time for the phenomenon of free charge carriers to be generated. Next we are looking into a thermocouple. A thermocouple basically consists of two dissimilar metal wires. As you can see here, there are two wires. One is this upper length in which we have connected a voltmeter, and then there is another wire which is at this lower length, and both of them are joined here. Two junctions are there, and what we find out is that if one junction is heated up whereas the other junction is kept very cold, then there will be a current flowing through the wires, which is basically through the Seebeck effect, and because of that flow in current you will find out that there is a voltage difference between this junction and this junction, and that is given by that is measured by this particular voltmeter. So this Seebeck effect is basically generates the thermal electromotive force, because of which the charge basically concentrates in one region and it is removed from the other region. So what happens in a Peltier-Seebeck effect is, when one junction is cold, the amount of free carriers there is less, and when the other junction is hot, the carrier concentration is more, because of which in one place the charge carrier concentration is more than the other, because of which there is a potential difference or a flow of current, and that is basically what is used to measure the temperature. So here you can see that it's not an absolute measurement, it basically depends on what is the difference between these two. So the reference junction, which is the cold junction, has to be kept at a constant temperature, a low constant temperature, and this temperature is basically the hot temperature, which varies with respect to time, and the voltmeter basically gives a difference between these two. So here this reference has to be always kept at a constant. Okay, so thermocouples makes use of the Peltier-Seebeck effect. Thus, when one end is kept constant at a certain temperature, it is important that we should keep kept constant. Normally at 0 degrees Celsius, the other end is exposed to an unknown temperature, and because of which there is an electromotive force that is generated, which can basically measure the temperature difference between the 2 points. The figure here shows the thermocouple, and this is the device that is dipped into the made in contact with the object of which we want to take the temperature. So what are the advantages? That it is self-powered and requires no external power supply. If you remember, the RTD always required an external current source to detect the temperature, whereas here there is no external power supply required, because whatever is basically generated from the temperature difference itself. It is a simple, rugged and inexpensive material or inexpensive sensor that is very commonly available, and it can withstand harsh environment. The disadvantage is that it is non-linear. That means that the Seebeck effect itself is non-linear. That means with respect to temperature, the carrier concentration change is not linear. Means the difference is not linear. If suppose the temperature changes from 10 degree to 20 degree, and we have, let's say, 10 raised to power 11 carriers generated, and the next 30 degree difference, suppose the charge carrier is 10 raised to power 12, so 40 we will automatically expect that it should be 10 raised to power 13, but it may be sometimes 10 raised to power 14. So the change is not linear. That is what is non-linear and requires a cold junction compensation for making it linear. It is not as accurate as RTDs or thermistors, and it is less stable and also less sensitive. Next we will look into the thermistor. The thermistor is basically like RTD. It is also temperature sensitive, but it is not actually a wire. It is basically an electronic component that exhibits a large change in resistance with change in body temperature. So an obvious question that people will have is, what is the difference between basically RTD and thermistor? The difference is that length of wire that I was talking about. In RTD, the length of the wire had to be too large because the effect that we are basically using there is different. Here what we have is basically metal oxide semiconductor material, which is very sensitive to temperature. It's highly sensitive to temperature variation, and that's why sometimes thermistors are also called as temperature sensitive resistors. Okay, and if you would look at the response time of the thermistor, the response time of the thermistor is very, very fast as compared to the RTDs. Okay, but the range of temperature in which they operate, that is not very large. In RTD you could go up to large temperature variations, whereas in thermistor the range of temperatures that you can measure, that is not very large, but the response time is very fast. Some of the available thermistors in the market is shown in this figure here. So the advantage is that it is inexpensive, it is rugged and reliable, and the response time is very quick. That is the second advantage. The disadvantage is that it does not measure very long temperature differences. If you would compare it with RTD, you can see that in RTD the range is very, very large. It goes up to 800 degrees Celsius. So here the disadvantage is that the temperature range is very small and the signal is not linear. As I told, the change is not linear, it is non-linear. And then the thermistor, again, just like RTD, it also basically has some current flowing through it, and some power supply has to be there attached to the thermistor for checking the change in current. So that will make some kind of self-heating phenomenon in the thermistor, because of which the temperature reading may be slightly wrong. Then why is basically thermistor used? One of the major reasons is this fast response of the thermistor. Next we look at the sensors for measuring light or detecting light. So you should understand what is detecting light and what is measuring. Measuring is when we try to measure how much is the light. Detecting is to just check whether there is light or not. Photoresistors is one of the light sensors, and as the name suggests, photo is basically for light and resistor is basically for resistance. So when light falls on certain material, the resistance of that material basically changes. The photoresistors are also sometimes called as LDRs or light dependent resistors. and it is very much used in robotic and small experiments, wherein light detection is one of the major requirement. So it basically consists of some photodetector material, okay, that basically absorbs the photons that are coming to it, and basically converts it into current. How does it do that? One of the examples is, you might have studied in the case of PN junction. A PN junction basically works on the principle that how much current, forward bias current, is there so that the junction basically disappears. In in LDR, basically the semiconductor PN junction will have a large junction at the PN junction. The width of the junction will be large, and that is the area that is exposed to light, and because of the light energy that is falling on the junction, new carriers are generated, because of which the flow of current that is through the the PN junction is different, and that is basically the principle for LDRs. Next is phototransistors. Phototransistors is similar to photoresistors, the same semiconductor material, but instead of the junction of a PN junction, for the case of phototransistors, we are basically having this was for the case of photodetectors and photodiode. The previous one was photodiode, this one was photoresistor. So photodiode basically has this PN junction, whereas the transistor has again junction, but in transistor you all know that it is PN junction, so there are two junctions are there. So phototransistor is similar to that of photodiode, okay, but obviously phototransistor gives a much larger current output as compared to a photodiode. So in light sensors we have studied photoresistors, photodiode and phototransistors. Next is the position sensors. Already we have studied position sensors. Some of the position sensors we have already studied. There are three types of position sensors. One is the inductive sensor, then capacitive displacement sensor, and third is the magnetostrictive sensors. The inductive sensors we have already studied, the LVDT and the RVDT. So there is no point in repeating the same portion here. You can understand it by looking to the previous video. Whereas when we come to the capacitive displacement sensor, the capacitive displacement sensor basically works on the principle that one plate, if I am going to take two plates, two metal bodies or conducting bodies, and if I am basically charging one of them up, then the other body gets negatively charged based on what is the the gap between them and what is the epsilon value in between the two conductors. So if you are having an object which is conducting in nature, and on top of that, suppose if you put another plate which is charged, then there is a capacitive effect between these two, and the capacitive displacement sensor basically works on that. So capacitive sensors detect virtually any material. Okay, it can be cardboard, paper, plastic, up to a distance of 10 millimeter. They are also suitable for the detection of metallic or fluid objects. Okay. The good thing is that it offers a high speed or non-contact sensing at an extremely long life. One of the examples you can see is basically the screen of your mobile. The mobile phone screen, most of them basically works on the principle of this capacitive displacement. Okay, so the capacitive proximity sensors are designed to operate by generating an electrostatic field and detecting changes in this field caused when a target approaches the sensing phase. So whenever we are operating a mobile phone, this is the same principle that we are basically using, and basically the screen of the mobile phone or the smartphone. Okay, so it basically has a probe, an oscillator is there, a rectifier circuit is there, and finally the output circuit. The workings of this is basically explained as when there is no target, the oscillator is inactive. That means this does not work when there is no material in front. And when a target approaches, when there is a target that is approaching, the probe basically picks up that there is a target that has come, basically due to the change in electrostatic field. And that will basically send us, that raises the capacitance of the probe system, which basically starts this oscillator, and the energy of the oscillator is basically dependent on how much capacitance is there detected by the probe. As the capacitance goes up, the amplitude of the wave in the oscillator also goes up. When that goes up, when you have a rectifier circuit, the rectifier circuit basically rectifies and tries to find out what is the maximum amplitude of the signal, and here we will get the amplitude of the signal. So based on high capacitance, the amplitude here will go high. That is how we use the capacitive displacement sensor. As mentioned here, the capacitive displacement, the capacitance of the probe system is determined by the target's size, the dielectric constant of the material, and the distance from the probe. The larger the size and dielectric constants of a target, the more it increases the capacitance. See, basically what happens is, suppose you are having two charge plates like this. So this is positive, this is negative. So between them there is electrostatic field. Electrostatic field is basically the field that is there between two opposite charges. Now when any material, there is no material in between these two, then what happens is that the capacitance value between these two, the capacitance value is a certain calibrated value. Once you have any material, it may be metallic, it may be non-metallic, it may be conducting, non-conducting, whatever be the material, the capacitance changes because the epsilon value, because of this entry of the new material, that basically changes. And the capacitance of a capacitor, if you would see, it will depend on the area, the gap, and the epsilon value in between. So here that epsilon value is changing because of the presence of the material, and that's how it detects that okay, there is some touch that has come here, or there is some capacitance change that has come here. As I said, this is what is happening in your mobile screen also. So the more closer the object is to the surface, the more closer the object is to the surface, that much more the capacitive value, and that's how we actually find out the position of the object from the sensor surface. Next in the position sensor is magnetostrictive sensor. In magnetostrictive sensor, the change of the resistivity of a material, that is basically happening in the case of a magnetic field. The change in the resistivity of the material. How does the resistivity of the material of a or through magnetostrictive effect, how does the resistivity of a material change is that there are certain ferromagnetic material like nickel, iron and cobalt. The main fact of the magnetostrictive sensor or the magnetostrictive material is that whenever there is a magnetic field around these materials, these ferromagnetic materials, which are also magnetostrictive materials, these materials, when they are in the magnetic field, there is a change in shape. Okay, there is a change in shape. So the magnetostrictive materials basically converts the magnetic energy to mechanical energy, or vice versa. That means it can change the mechanical energy to magnetic energy also. So as the magnetostrictive material is magnetized, the change in shape or the change in size is basically there is a strain that is happening in the material, and that strain basically exhibits as a change in the length. Per unit length there is a change. Okay, so in this particular diagram you can see that suppose there is a coil here. This coil, when we pass current through it, whenever we know that when there is a coil like this, whenever we pass current through it, a magnetic field is generated in between this, the Faraday's principle, isn't it? So this magnetic field, it will enter this particular magnetostrictive material, because of which there is a deformation, and the deformation basically results in the elongation of the length of this particular wire. So what we are having here is, suppose there is a a magnet that is shown here, which is attached to the object whose position you want to measure. So when this sensor is when this particular magnet is here, a magnetic field is basically sent, and that magnetic field basically results in the constriction of the material. So suppose the magnetic field is active here, a change of length will basically happen. So it is just like a pulse the magnetic field will be given, and that pulse will basically make a change. A deformation will also be like a pulse. So it's like for maybe for a 1 microsecond there will be a change in the shape, and that change is again brought back. So what happens is, this change basically moves in both the direction. So that change in shape is basically a torsional wave, and that torsional wave moves in this direction as well as in this direction. This wave that is traveling in this particular direction, that is damped out by the damper, so this wave does not go further, whereas this wave that is traveling and coming here, that is measured using the measuring circuit. Okay, so when you send an excitation pulse, because of this change in the length, the torsional waves come, and with the speed of the torsional wave, we can basically measure how far away the change or the deformation has happened. And that deformation that has happened with the length of where it has happened, the position of where the magnet is, and with that the position of the object that we are looking at, that position can be sensed. So the magnet is used to produce a pulse of magnetic field, which will test the waveguide wire at the point where the target is. So wherever the target is, there the magnet is, and that magnet will produce a pulse of magnetic field, because of which there will be a stress in the waveguide wire. This is the waveguide wire. Okay, and this stress creates a strain pulse which travels at a speed. Okay, and the timing between the pulse and the pickup is measured, and based on that we basically try to understand where the position of the target is. Another very much used position sensor is the magnetic sensor or the Hall effect sensor. What happens in a Hall effect sensor is, basically a material is there. In that material, if suppose current is passing through in this direction as it is shown in the figure, and there is a magnetic field that is applied in this material, then because of the Lorentz force, the electrons or the charge carriers that are present in this particular material, they will move towards one side. They will move towards one side. So magnetic sensors or Hall effect sensors, these produce output voltages corresponding proportional to the strength of the magnetic field. The Hall element or the Hall effect element is basically made up of thin sheets of conducting material, as you can see here. It may be conductive material or it may be even a semiconductor material. The output connection, that is this, are basically perpendicular to the direction of current flow. So if this is the direction of current flow, the output is taken perpendicular to it. And then when we are having a change in the magnetic field, so when there is a change in magnetic field, the Lorentz force basically acts, and that acts in such a way that the more charge carriers are deflected to one side. So in one side you will have the buildup of charge, because of which there will be a difference between these two ends. So at this end and this end there will be a difference, and that difference is basically given by the voltage of the Hall effect, so V Hall, and with that we measure how much amount of magnetic field is there. So if suppose you are having the Hall effect kept somewhere, let's say for the case of a disk, and we want to measure what is the position of this disk, so in one place we will attach a magnet, and here we are having suppose this Hall effect device which basically checks the Hall effect. Okay, so when this is coming closer to the Hall effect detector, the magnetic field will basically change, and when it passes through this, we will see that again it changes and it becomes less. So as the magnet is going around and coming back, when it reaches here, you will have the highest excitation because it is closer to the magnet is closer to the Hall effect device or the Hall effect sensor, and because of which you will basically have a pulse like this. So wherever the highest value we are having, at that point this particular magnet was the closest. So if suppose the disk is moving for 10 times, then we will have 10 different pulses, and we can look at the pulse and we can say what is the position of the magnet, with that what is the position of the disk, that is the angular position of the disk, and we can even measure the velocity. Next we are going to look at strain gauges. What are strain gauges? Strain gauges is something that has been used for a very long time. The strain gauges, they have been used for pressure sensor, for load cells, torque sensor, and also as position sensor. So what is stress? Stress is defined as the object's internal resisting force. So suppose if you are having a material, suppose a conducting rod like this, then if suppose some force is applied on it, then the material basically opposes that force. That force is basically called as the stress. And strain is defined as the displacement and deformation that occurs. So suppose if you are trying to bend this, so it goes that there is a strain that is happening. So when external forces are applied to a stationary object, the stress and the strain are the result. Stress is the resisting force and strain is the deformation that has occurred. The strain itself consists of tensile and compressive strength, okay, which are basically shown by the positive and the negative sign. So when we are talking about a strain gauge, what happens in a strain gauge is, due to the pressure or due to the force that is applied, the material undergoes a stress and strain, because of which the length of the material changes. And we know that if there is a conductor which has a particular area of cross section and there is a length L, okay, there is a length L, and the material characteristics which is written as the resistivity rho, okay, the resistivity rho. So these three things basically decide what is the resistance offered by this particular conductor whenever there is a change in these particular values. So these three decide what is the resistor. Whenever there is a strain or a stress in the material, the length of the conductor changes, and obviously the area also changes. So the area may become less, the length may become more. So if the area becomes length becomes more, and the area becomes less, then obviously the resistance of the wire will basically change. So as you can see, the wire is wound in such a way, and whenever there is a stress, the length of this particular wire changes, the area changes, because of which the resistance of this particular conductor changes. And this can be detected with the help of a bridge circuit. So you can see here, the electrical students or the electronic students might have learned, or even in 12th standard you might have learned what's a V-Stance bridge. So in this V-Stance bridge, the value of the resistance R1, R2, R3 and the resistance offered by the strain gauge is such that the bridge is balanced and there is no voltage across the junction, or there is no current flowing through this bridge, through this Wheaton's bridge. There is no current that is flowing. So in that case, when the current is zero, we say that the bridge is balanced. So initially, when there is no stress, or there is no force, or there is no pressure applied on this particular strain gauge, there is a resistance, and the value of R1, R2, R3 and R are chosen in such a way, not R is fixed value. The resistance value R1, R2, R3 are chosen in such a way that the bridge is balanced and the current is zero. Whenever there is a stress or a strain experienced by this strain gauge, then the resistance value changes, which basically disturbs the balance of this Wheaton's bridge, because of which some current flows through the bridge, and this current is detected and calibrated to find out what is the strain that is experienced by the strain gauge. So by carefully calibrating, we can find out the strain that is experienced by this strain gauge. So we calibrate the voltage by carefully calculating what is the force. We basically try to convert this voltage reading into the reading of the strain. So these are the different sensors that I had discussed for basic fundamental sensor methodologies, through which we are having different sensors. Why this is explained to you in this particular module is, whenever you go to purchase a proximity sensor or a pressure sensor or a temperature sensor, you should basically understand what are the basic working, what is the basic working of that. Now you can explore more and then try to see which kind of sensors will suit you most, cost wise also, and the response time, all these things. So next what we will discuss is, when we try to choose the select a sensor, how we will do that we will see in the next class. Thank you.